Hello everyone, I am Dr. Nitin Kumar Saxena. In this video lecture, we will discuss the concept of capacitor and capacitance. To begin with, the concept of capacitor and capacitor, let us we have a conductor A and a conductor B, right? Suppose we have two conductors and the charge on the first conductor is Q1 while the charge on the second conductor is Q2. So what will happen if we have two conductors, or we can say any metal surface having the charge Q1 and another surface or a metal or a conductor having a charge Q2. Both the surfaces are placed at some distance, suppose D. Now, if this metal or this conductor has a charge Q1, what will happen? The charge will appear on the outer surface. This we have studied that whatever a charge any metal body has, it appears on the outer surface of the metal. Similarly, the charge on the surface B will also appear like this. Okay. So, you see, if the arrangement between the two metals or two conductors or two surfaces are like this, that the surface A has the charge Q1 and surface B has a charge Q2. So what will happen? To make this arrangement, we want to make these two surfaces at a distance of D. So for keeping this, what we have to do? We have to do some work so that it will remain in this position, right? And if I am saying the voltage at this is V1 and voltage is this V2, so the potential difference between the body A and body B will be V1 minus V2. So this will be the potential difference between these two bodies or metals or surfaces, and the value is given by V1 minus V2. So you see, when the body has a charge Q1 and another body having the charge Q2 are separated by some distance, they will store a kind of energy in it, and this energy is called electrostatic energy. Why? Because these charges are in static position. In the same way, if we are designing the body in such a way that, like I am saying, okay, we are supplying the charge to the body, and the body, this when we are supplying the charge, so what will happen? Like if body A is if body A is charged by the plus Q1 charge, and suppose the same charge is appears but opposite in direction at surface B. Suppose we are supplying this charge from any external system, any external battery. So what will happen? The external system is giving the charge plus Q1 to suppose the body A, and plus the same negative charge to body B, and both the bodies are at distance D. So what will happen in making this arrangement? Some energy will be stored between the body A and body B, right? Since this energy is due to the static positions of the charge, so this is called electrostatic energy. And if we have such type of arrangement, then this body is called a capacitor. So we can again review our whole discussion that if we have two bodies or two conductors or two metal surfaces having equal and opposite charges, then they will store some kind of energy. This energy is called electrostatic energy between them, and the body, since having the energy stored in it is electrostatic energy, so what we say? We say this body as a capacitor. Alright, so in general we can say a capacitor can be defined when the two conductors are placed at some distance and having the equal and opposite charge on these two surfaces, right? So such type of arrangement is called capacitor, right? The surface may be of any shape. It is not necessary that I'm representing it like this, but it is not necessary that it would be like a line. Line means a plate. So it may be like this, it may be any surface like this, or any kind of surface. It may be like this also, right? So any two conductors, irrespective of their shape, dimension, if they carry equal and opposite charge and are separated with each other, they form a they they have energy stored in it, and this energy is called electrostatic energy, and such arrangement is called capacitor. Such arrangement is called capacitor, and the this device value, which we will see later, is called capacitance. So let's have a suppose I am saying, okay, if I am saying we have two bodies like this. Suppose I am saying body A and body B, right? This body has plus Q charge and this body has minus Q charge. So what will happen? This Q charge will come at the surface here, right? At the same time, the negative charge will appear at this outer surface because they both are in opposite directions. So they will try to attract each other, and hence the charge on body A or surface A will come in this side, and charge on B will come on this side. Okay. So if you see this structure, so what you will get, yes. Now you see, this means if surface A has plus Q charge, so equal and opposite charge minus Q will appear at B, and this arrangement is called as a capacitor, right? Now if I am saying, okay, let me write its definition first. So capacitor is defined as a separation of two equal and opposite charge conductors. This carries, or this stores energy in the form of electrostatic energy. Hence, we can conclude finally that if we have the two conductors having equal and opposite charges and they are separated with each other, then they form a capacitor. And in this capacitor, the energy is stored in the form of electrostatic energy. Electrostatic energy, right? Now, if I am saying that if we have only one conductor, does it form a capacitor? If I am saying I am having only one conductor A with plus Q charge on it, so will it form a capacitor? From our previous knowledge, we know that if a charge single charge exists, then their opposite, equal and opposite charge exist at infinity. So if plus q charge exists at this point, so we can assume that we can consider that its equal and negative charge, equal and opposite charge will be at infinity, and hence this will form a capacitor with positive plate here and negative plate or negative surface at infinity, right? So in this way we can define the concept of capacitor. Now see, if again I am drawing this again, and you see here for the surface, if I am say the surface A or metal A, this is metal B having charge plus Q, this having charge equal and opposite minus Q. Here suppose the voltage is VA, here the voltage is BV. So the what is the value of potential difference? The potential difference, suppose I am saying it B is given by VA minus BV. Right? Now you see, you know the electric field lines goes from positive charge to negative charge, and hence here we can say that electric field lines will go from this surface A to surface B. Now the magnitude of this E will depend on the amount of the charge, right? This means if we have more charge, this means more E, less charge means less E. At the same time, you know the formula that E is given by B divided by D. The potential difference and the separation between these two surfaces, okay, will give the value of electric field by the formula E is equals to V upon D. This means you can say here that this E is directly proportional to V. And what we have seen here, that Q is directly proportional to E. More charge means more electric field, less charge means less electric field. At the same time, you see here, more electric field means more potential, less electric field means less potential. And hence, if I combine these two equations together, I can say, what I can say? I can say that the Q is proportional to V. I can say Q is proportional to V. Means if we have the more charge at the surface A and B, the potential difference will be more between this structure. If I use a constant here, so I can write the Q is given by CB, where C is a constant and called capacitance of the capacitor. Okay, what we are saying, this structure having metal A and metal B, or conductor A and conductor B with charge plus Q and minus Q. So this structure we have defined it as a capacitor, and the magnitude of this, the value is defined as a parameter C, which is defined as capacitance. So what is capacitance? If you see the value of capacitance, so capacitance is Q upon B. This means the capacitance of a capacitor is defined as the ratio between Q and V. So I can write here, so I can write here that the capacitance of a capacitor is defined as the ratio of Q, charge and potential. Okay, So the capacitance C is defined as the ratio between Q and B. If I go for the unit of C, so what I can say, C is Q upon V. You know the unit of C is coulomb, the unit of voltage is volt. So the unit of C is coulomb per volt. In short, we write it farad and denote by F. So the unit of C, the unit of capacitance is given by farad, right? Now you see the one concept here. If I want more C, if I want more C means I have a capacitor and I want the value of this capacitor, so the capacitance value of this capacitor should be more. How can I get it? I can get it by managing the ratio of Q and B. Right? This means for getting more C, what I will do? Increase Q and decrease V. Right? According to mathematical formula, for getting more value of C, we have to increase value of Q and decrease the value of B. But as I told you that Q is given by E and E is given by B. So this means the increase in the charge, will increase the electric field between the bodies, between the surface A and B, and this increase in electric field will increase the value of voltage. So we can increase these values up to some extent. Now see the next concept. If I am saying that okay, if I am increasing the value of electric field, okay, if I am increasing the value of electric fields between the surface A and B, suppose I am denoting like this, here plus Q, here minus Q. So what I am doing, I am increasing the value of charge, right? So I am increasing the value of electric field, and since I am increasing the value of electric field, B is also increasing, and hence the increase of the value of capacitance will depend on the value of electric field between these two surface A and B. Right? Now you see what will happen if I am going to increase the value of electric field. When we are going to increase the value of electric field between the surface A and B, what will happen? There would be some air between these two plates. Okay. So, on increasing the electric field, what will happen? With this air, with this molecule, air molecule, what will happen? If we are increasing the value of electric field, this air molecule ionized will ionize. Why it will ionize? Because we are increasing the value of electric field, and on increasing the value of electric field, every molecule has atom, and atom has nucleus positively charged and electrons which are moving around this atom. So what will happen? This positive and negative charge will try to separate because of this electric field in such a way that the positive particle will try to move this side and negative particle will try to move this side, and hence we can say if we are going to increase the value of electric field continuously, what will happen? The air which is existing between the surface A and B will ionize, and when it will ionize, then what will happen? If it will ionize, then this path which was non-conducting in starting, now it will be a conducting path medium. It will provide conducting medium after ionization of air. Okay, so after ionization of air, what will happen? This air will be ionized and it will form a conducting path between A and B. Then what will happen? This plus Q charge and this minus Q charge will move. And if it will move, the concept of capacitor will vanish, because what is the concept of capacitor? That the equal and opposite charge should be placed at some separation, and there will be no separation, and hence if this air becomes ionized, this means it will not form a capacitor. So the important condition is that whatever the medium we have between A and B, that should not be ionized, right? So if we are taking the air, so it should not be ionized. For understanding this, that at what value of potential, at what value of electric field the air will not ionize, we give the concept of dielectric strength. We give the concept of dielectric strength. Okay, so what is dielectric strength? Dielectric strength means the value of any medium, up to which this medium will not be ionized. If I am saying air, then for air, this E is given by 3 into 10 to the power 6 volt per meter. Means if we are applying for unit distance of 1 meter, if we are applying electric field of value voltage 3 into 10 to the power 6 volt per meter, means between these two points, the potential difference is 3 into 10 to the power 6 volt, and these 2 points are separated at 1 meter. Up to this point, the air will not ionized, right? And if we are increasing this potential difference, then it will be ionized. Since the plates of capacitor are separated, but the separation is very less, at the order of 1 millimeter, or right. So if I change it to millimeter, or let me allow to write it in centimeter, so this means if I am providing a potential difference between A and B of the range of 3 into 10 to the power 4 volt per centimeter, means if the separation between A and B is 1 centimeter and I am applying the potential 3 into 10 to the power 4, then up to this value air will not ionize. If I am increasing the potential more than 3 into 10 to the power 4, then the air will ionize and it will not form a capacitor. So in other words, we can conclude that if we have a capacitor, and air is filled between the surface A and B, which are at distance d, so we have to keep in mind that it should not cross to its dielectric strength. And how can we find the value of dielectric strength? If air is filled between A and B, then its maximum potential difference will be 3 into 10 to the power 4 volt per centimeter. Okay, so if I want to increase the value of this potential difference between A and B, I can move on different dielectric materials, which I have told you in previous video that what is the concept of dielectric materials. So in place of air, we can go for different type of dielectric material, right? Is it okay? And one more thing that I have given, the unit of capacitor is 1 farad. So this farad is a very big unit. In real life, the capacitance value is very small compared to farad. the capacitance available in market are of microfarad or picofarad range. You will never find a capacitor of the value of 1 farad. The available in market is of are in the range of microfarad or in picofarad. How is it that we will see in later on? So up to this point, we will like keep in mind that a real capacitor value, the capacitance value in real, may be in the range of either microfarad, nanofarad, or picofarad. What is this? 10 to the power minus 6 farad, 10 to the power minus 12 farad, and if I talk about nanofarad, then 10 to the power minus 9 farad. So this is the realistic range of available capacitors in market. Okay, so like in general, if anyone asks that what may be the value of capacitance, so the value of capacitance practically may be in microfarad, nanofarad, or picofarad, right? So also the if we talk about the symbol of capacitor, so the capacitor is normally denoted by this symbol. Okay, so this is the representation of any capacitor. If the value of capacitance is variable, so we denote like this. This arrow denotes that our capacitor has the variable value of capacitance. So this type of symbol, the two plates, vertical plates, are used to denote, to represent the value of capacitor in any circuit, right? So after this discussion, let us move on some mathematics about the capacitor, and we start the formula for parallel plate capacitor. Okay, as I have told you that the capacitor can be designed by using the two metal surfaces of any kind of shape. So this is the most general thing. So let us move on the first topic, that if we have a capacitor in the shape of parallel plate, and this is the most commonly used type of capacitor, right? So if I am saying this, you see, is a plate, right? So there are two plates which are something like this. The surface A is a plate A, surface B is a plate B. So I am saying this is plate A, this is plate B. So this is surface A, this is surface B, and I am saying, since this is two-dimensional figure, if I talk about this metal surface, so a plate, so I'll define its surface charge density plus sigma, and if this is plus sigma, then the surface charge density for plate B is minus sigma, and both the plates are separated at a distance of d, and the cross sectional area for this plate is A, right? So if you are confusing with this 2A, so we can say we have two plates P and Q, right? So we have two plates P and Q. Plate A has surface charge density plus sigma. Plate Q has surface charge density minus sigma, right? This means both the plates has equal and opposite charge, and both the plates are separated at a distance of d, and the area of each surface is given by capital A, right? Now if I am assuming this area is much greater than D. Okay, so this parallel plate capacitor, the surface of the plate has area A, right? So if this is A, this is also A, and the separation between these two surfaces is given by D, and the value of D is very less compared to this A, right? So this we are assuming, right? And if I am saying this plate is very big, infinitely long, so what will happen? The electric field line will go like this, because this is plus sigma, this is minus sigma, right? So if I'm saying the area of this plate is A, so the charge on this will be given by, the charge of this will be given by sigma times A, and here the charge is given by minus sigma A. Okay, the charge on the surface Q, again on surface Q, again if you are confusing with two Q's, so you can again say this 1 and 2, right? So surface 1 and surface 2. Surface 2 has charge minus sigma A, surface 1 has charge sigma A, right? Where sigma is the surface charge density and A is the area of the plate, parallel plates, right? Now you see, another concept comes before discussing the whole concept. We will say a concept of fringing. What is fringing? You know, if this plate has plus Q charge and this has minus Q charge, so what will happen? Electric field line will move like this. But what will happen at the corners? At the corners, the electric field lines will go like this. Okay, so we can say if we are at the corner of these two lines, what will happen? The electric field lines are not uniform like this, but it will be like this. So this is called fringing. This is called fringing. This is called fringing, and this effect is called fringing effect. That if we have two surfaces, then between the surface we can assume that electric field lines will be uniform and will move from positive to negative. But what will happen at the corners? At this corner, the electric field will not be like this uniform. It would be like some different shape from the positive plate to negative plate, and this effect is called fringing effect. So we are again assuming the second concept, which we are assuming that we are neglecting fringing effect. We are neglecting effect. Okay, so what are the two assumptions which we are taking for driving the expression for capacitance in case of parallel plate capacitor? Number one, the area of surface 1 and surface 2 is A, and the separation between the surface 1 and surface 2 is D, in such a way that area is much greater than D. And second is, we are neglecting the concept of fringing at the corners of these parallel plates, right? So after getting these two assumptions, you see, you consider the 3 points, 1 point here, 1 point here, and 1 point here. This means a point just after the positive plate, outside of the positive plate, a point between the positive and negative plate, and a point between the after the negative plate. So you see, if I am saying, okay, at this point, suppose I am saying this point is X, this point is Y, and this point is Z. So at point X, what will happen? This plus Q charge if I want to know the value of electric field at point X, then what will happen? At this point X, electric field due to 1 will be outside, because we can assume here plus 1 unit charge over here to get the value of electric field. So this is positive charge, this is plus 1. So what will happen? It will be outward. For this, it will be this side, right? Due to E2. Similarly here you see, again I am supposing the plus 1 to get the value of electric field at point Z. So the plate 1, surface 1 will repel it. Okay. So if it repel it, then this value will be E1, and plate 2 will attract it, so this will be E2. Right? And what will happen at Y? At Y, plate 1, again I will suppose a plus 1 over here. So at 1 will repel it and 2 will attract it. Right? So what I can conclude? I can conclude here that at point X, E1 minus E2, right? I am taking the magnitude only, right? Because directions are given there. So this E1 and E2 are the magnitudes, right? If you are confusing, then you can write like this also. Okay, in short, I am writing E1 minus E2. At point Y, E1 plus E2. At point Z, E1 minus E2. So this will be the value of electric field at point X. X is a point which is outside of the positive plate. At point Y is between the plate positive and negative. And at point Z is outside of the negative plate. Right? Now we will try to find what is the value of this E1 and E2. From the basic knowledge of this plate, suppose if this plate has plus sigma value, then the value of electric field E is given by the formula sigma upon epsilon naught. This we have studied, sigma upon 2 epsilon naught. This we have studied when we were discussed the concept of Gauss theorem, and using the Gauss theorem we try to find the value of electric field at the point near to the parallel plate, infinitely long parallel plate. So we have, in starting we have taken that A is very much greater than D, so we can consider it as a infinitely long parallel plate, and hence the electric field at any point near to this parallel plate is given by the formula sigma upon 2 epsilon naught. So you see this value is due to this plus charge, so I am saying this E1, this is surface 1, and similarly if this is the surface 2 with minus sigma, so value is given by sigma upon 2 epsilon naught with minus value. Okay, so if this is plus charge, then this value is in plus. If this is negative charge, then this value is in negative. And since we have already taken the direction here, so what we will say, since this negative charge and this positive charge is to define the direction only, and direction we have already taken here. So this means the value of E1 is sigma upon 2 epsilon, and the value of E2 is also sigma upon 2 epsilon. Why? Because we know this E2 is in negative, but we have already taken here negative. You see, we have already taken the direction. This direction is due to the negative charge, this direction is due to the positive charge. So we cannot take the direction 2 times. Okay, if we have already taken, now we will take only the magnitude, which I told you here that we will take only the magnitude because we have already taken the negative sign. So sigma upon 2 epsilon naught minus sigma upon 2 epsilon naught, that will be 0. Here sigma upon 2 epsilon naught plus sigma upon 2 epsilon naught is sigma upon epsilon naught. And here sigma upon 2 epsilon naught, sigma upon 2 epsilon naught again 0. So finally what we find? We find that if I'm talking about the electric field value outside of this plate system, either this side or this side, the value of electric field intensity, the magnitude of electric field is 0. But when we are talking about the electric field between this, the value is given by sigma upon epsilon naught. Right? So finally we can conclude. What we can conclude? So we can conclude here that the electric field outside of this parallel plate capacitor will be 0. Okay, the electric field outside of this parallel plate capacitor, because this is parallel plate capacitor, so outside of this, both the side, electric field will be 0. But the electric field inside the parallel plate capacitor is given by E equals to sigma upon epsilon. Okay, so in this way we can get what is the value of electric field. Okay, I am writing here again. So the value of electric field, between these two plates of parallel plate capacitor is given by sigma upon epsilon naught. Since we know the sigma is given by QA, so what can I write here? QA upon epsilon naught. Right? If this is the value of E, then what will be the value of V? We know this formula, sorry. Uh, Sorry, this something I wrote wrong. The sigma is surface charge density. Surface charge density is defined as charge per unit volume. So please correct it. I think I wrote here QA, sigma is QA. So please correct it. Okay, sigma is Q by A. So what will be this? This will be Q by A. Sigma is given by surface charge density is given by charge per unit area. So please correct it. So sigma is Q upon epsilon naught A. So what is the value of V? V is given by ED. So QD upon epsilon naught A. Right? So this means for parallel plate capacitor, the potential between the two plates is given by this formula. Right? And from the definition of capacitor, you know that Q is given by CB, right? So what is Q here? Q is, if I find the value of Q from this definition, epsilon naught A upon D into V, right? and hence C is given by epsilon naught A upon D. So this is the value of capacitance. This is the value of capacitance for a parallel plate capacitor. So if we have a parallel plate capacitor, the capacitance between these two plates is given by epsilon naught A upon D. So I hope this point is clear. How can we get the value of C, capacitance between the parallel plate capacitor? Now see one understanding type question. If I am saying, if I am putting, okay, if I am having the formula C is epsilon naught A upon D, I know that if epsilon naught value is given by 8.85 into 10 to the power minus 12, right? If I want 1 farad capacitance and the separation between these two plates is given by 1 millimeter, so what will be the value of A here? A will be 1 multiplied with 10 to the power minus 3 divided by 8.85 into 10 to the power minus 12, right? So when you solve this, you will get 10 to the power 9 upon 8.85, right, meter square. Okay, you know 1 meter is 1000 kilometer, so I can write this 10 to the power 9 upon 8.85 into 10 to the power 6 kilometer square, 1000, right? So 1000 divided by 8.85. For simplicity, if I take this 10 divide by 10, what I will get 100, approximately 100 kilometer square. This for simplicity, what I am doing, I am taking this 8.85 equal to 10. So if this is 10, so what we will get 100 kilometer square. So this, what is the physical significance of this derivation? The physical significance is, if you see, if you have a capacitor in which two parallel plates are separated at a distance of 1 millimeter and you want to maintain the capacitance value 1 farad, then the size of the plate will be 100 kilometers square, which is practically impossible, right? And hence we can say we cannot define a capacitor with value of 1 farad. So before this discussion I told you that why the value of capacitance cannot be in the range of 1 farad. Okay, so this is the reason that no capacitance can have a value in the range of farads. Okay, because if we want this is not practically possible, because in that case the area of the parallel plate capacitor should be 100 kilometers square, and practically it is not feasible. If you want exact calculations, so you can go for exact calculations also, right? So I am giving you only the concept. If you want to know the exact calculations, you can go and you can find what would be the value of exact area from this formula. So I hope this point of parallel plate capacitance is clear to you. And after this, okay, in this video I'll stop at this point. In next video we will discuss the value of the capacitance if I have, in place of air, I have any dielectric medium. So what would be the effect and how the formula will change if I have a dielectric material between these two plates. Okay, so in this video we stop at this point. Thank you very much.